So far, we have explored the physical layer, which deals with the raw transmission of bits. Up in the hierarchy, the next logical layer is the data link layer. This will be our primary focus for this module. The data link layer is where we receive the raw bits and transform them into uh, meaningful or reliable units of information. Our discussion will be on these fundamental processes, the framing, flow control, and error control. So before we begin, let's look at the concepts we'll be covering. First, we will establish what framing is and explore the different ways we define a frame boundaries. From there, we will transition to flow and error control. Flow and error control mechanisms guarantee the efficiency and uh, integrity of our data transmission. So next we will see various error detection and correction techniques. And then finally, we will discuss the different services and protocols that the data link layer offers to the layer above it, the network layer. So we'll begin our discussion on framing, starting with its purpose and types. At the physical layer, we are simply concerned with the movement of continuous bit stream, the zeros and ones. The data link layer's first critical task is to break this stream into smaller, manageable, and discrete blocks. So we call this process as framing. You can think of a frame as the fundamental unit of data transfer at the data link layer. Each frame is a self-contained packet of information. It can be distinguished by two components, the header followed with the data, and then you have a trailer part. The trailer holds a checksum for error checking or error detection. So this structure helps the receiver identify where one block of data ends and the next block of data begins. The two main approaches of this are fixed size framing and variable size framing. Fixed size framing frames have a predetermined constant size, and variable size framing requires a mechanism to define the end of one frame and beginning of the next frame. So the simplest framing method is fixed size framing. In this approach, every single frame has a fixed constant length. This offers a significant advantage in terms of simplicity and predictability. The receiver does not need to look for a special character or a bit pattern to find the end of the frame. It simply counts a fixed number of bytes or bits and then realizes the starting or ending point of a frame. This method is particularly well suited for high speed networks that handle real time traffic. This is because the consistent frame size helps ensure low and predictable latency. A prime example is asynchronous transfer mode, the ATM, uh, where it uses a small fixed size unit called a cell to maintain a constant data flow. Some of the disadvantages are potential wastage of small data payloads, and then it requires fragmentation for large data, adding overhead. Also, it is less flexible for varying data sizes. So the ATM cell structure have a 5 byte header followed with a 48 byte payload. So in total, ATM cell will have 53 bytes, which is fixed size. So next we'll explore character oriented framing or variable sized framing. Also we'll see a special technique called byte stuffing to uh, facilitate data transfer without any conflict. So now in many scenarios, the data packets have variable lengths. For this, we use variable size framing. It requires a specific mechanism to indicate the frame boundaries. The first method is character oriented framing. Here, a special flag character is used to mark the beginning and ending of a frame. A significant challenge arises, however, if this flag character appears within the data itself, a problem known as data transparency. The solution to this problem is a technique called byte stuffing. The sender stuffs an extra escape character in uh, in the front of a data character whenever it is identical to the flag character. So for example, if you determine that the escape character is having 0 followed with 6 ones and then a 0, assuming that this is a bit pattern representing an escape character, and if the same sequence appears in the data, then it will have to be prefixed with an extra escape character, so that the first escape character indicates that the subsequent character should be treated as a data instead of treating it as a delimiter. Upon seeing the escape character, the receiver device knows to ignore it. It then treats the next character as part of the data. This preserves the integrity of the frame boundaries. So the process include at the sender's end, the data will be scanned for uh, bit patterns that exactly match the bit pattern that you are using for escape character, and then every such bit pattern should be prefixed with an additional escape character. Insert escape character before each escape character again, and then transmit stuffed frame. At the receiver end, scan the escape characters, remove escape, and treat the next character as data, not a delimiter. Continue until the actual flag is found. Extract original data. We will now examine the principles of bit-oriented framing and its corresponding bit stuffing technique. So on the same principle that we applied byte stuffing, bit-oriented framing operates at the bit level. This method uses a specific bit pattern, typically 0, 6 ones and then a 0, as the flag to signal frame boundaries. To handle data, we use bit stuffing. The idea is simple. After any 5 consecutive ones in the data stream, the sender inserts a 0 to ensure that the flag pattern can never accidentally appear within the payload. The receiver performs the inverse operation. It scans the incoming bits. When it detects a sequence of 5 consecutive ones, it automatically removes the following 0. This process is implemented in hardware and is highly efficient. So this extra stuffed bit is removed by the receiver, and this guarantees that the flag field sequence does not inadvertently appear in the frame. So we will compare two key flow control protocols, the stop and wait protocol and the sliding window protocol. But before we compare the flow control protocols, we'll take a look at two crucial mechanisms, the flow control and error control. As we move on from framing to the data transmission, we encounter two major challenges. First, what if the sender is much faster than the receiver? So we need to control the rate at which the sender and receiver uh, exchange the data. The receiver's buffer could overflow uh, as a result if sender sends the data at a faster rate, leading to data loss. So that this is why we need flow control, a mechanism to manage the data transmission rate. Second, the physical medium is prone to noise and external interference. This can corrupt the data, and then this necessitates the error control. So it is the set of techniques we use to detect and in some cases correct those uh, uh, errors. Together, these two mechanisms transform an unreliable physical medium into a reliable logical channel. Error control may include error detection for identifying corrupted frames and error correction for fixing corrupted bits or retransmitting the frame. It utilizes ARQ, the automatic repeat request, sorry, mechanisms. Now we'll compare uh, two flow control protocols, the stop and wait and the sliding window protocols. The most basic is the stop and wait protocol, where the sender transmits a single frame and then pauses waiting for an acknowledgement. Uh, this approach is highly inefficient as it leaves the channel idle for a significant amount of time, especially over very long distance links. A much more efficient solution is the sliding window protocol. This protocol allows the sender to transmit multiple frames in a pipeline before receiving an acknowledgement. The protocol uses a window of allowed frame numbers. This keeps the channel busy and improves the overall throughput. So it is therefore suitable for modern high-speed networks. So as part of flow control, the receiver monitors the buffer status. It sends flow control messages, for example, acknowledgements or stop signals to the sender. And then the sender adjusts its transmission rate based on these messages, preventing any data loss or overflow of data in the buffer. We'll now look at how we handle errors using the automatic repeat request protocol, ARQ. When errors happen, we need a method for recovery. The most common and robust approach is the automatic repeat request. ARQ is a cooperative process between the sender and receiver. It works by combining three elements: a method for error detection and a way for the receiver to signal that a frame is corrupted. The receiver can use a negative acknowledgement NAK or simply not acknowledge the frame. The third element is a retransmission mechanism at the sender. This also requires sequencing, and the sequencing involves numbering the frames in a sequence. This will ensure that frames are processed in a correct order. It also allows for correct handling of duplicate or lost frames. So when a frame is transmitted from sender to receiver, in the event of a transmission error, the receiver may send a negative acknowledgement. If the frame is delivered correctly, then it may simply acknowledge the frame, so that the sender will have an idea which frames are correctly delivered and which are corrupted during the transmission. So ARQ uses acknowledgements, timers, and sequence numbers to facilitate error-free data transmission. Next are the types of errors. There are two main types of transmission errors: a single bit error and a burst error. Errors can happen in different ways. A single bit error is when only one bit in the data unit is flipped. So you can see only one of the bits which was sent was flipped, the third bit. It while it can occur, it's relatively rare in most high-speed links. The more common type of error is a burst error, where two or more bits are corrupted. So you can see here multiple bits are flipped during the transmission. This is the original bit pattern, and this is the one that was received at the receiver's end. A burst can be caused by a single event, such as a sudden electrical spike, uh, and the external interference can cause a consecutive sequence of bits to be flipped. However, it is important to realize that the length of the burst in the span from the first corrupted bit to the last corrupted bit, it is not the number of bits actually changed. So the length is measured from the first corrupted bit to the last corrupted bit. Need not necessarily be consecutive. Errors within a burst may have gaps. So these burst errors are complex and complex to detect and correct compared to single bit errors. So these burst errors are common in practice due to noise bursts affecting a duration of transmission. Next is redundancy and coding scheme. Two main categories of coding schemes are block coding and convolutional coding. The only way to detect or correct an error is by adding redundancy to our data. This means we add extra bits to the original message. These bits do not carry any new information. Their purpose is to help the receiver verify the integrity of the data. Is the data correctly received or not? We implement this using a coding scheme. There are two major categories. One is block coding and second is convolutional coding. Block coding operates on fixed size blocks of data, while convolutional coding is a continuous process. So we'll first focus on block coding as it is foundational to many common protocols. So in block coding, we take a message of k bits called a data word. We add all our redundant bits to it. This results in a larger n bit unit, which is called a code word. The number of redundant bits r is simply uh, k plus r. So So the original data word is of length k bits. The redundant bits are added for error control, r bits. So the code word will have uh, k plus r bits in total, the transmitted block. The encoder is a device that performs this conversion. At the receiver, the decoder takes the received n-bit code word. If it is a valid code word from the predetermined set, it will be accepted. If not a valid code word, the error can be detected. So with k bits, you can have 2 raised to k combinations of data words. So these are the code words corresponding to actual data words. And then with n bits, you can have 2 raised to n combinations. So because the mapping is 1 to 1, the additional or invalid bit patterns can be recognized as errors during the transmission. So not all transmission errors can be detected. It may so happen that the flipped bits might accidentally represent some other valid code word. So such errors cannot be detected using block coding. A crucial property is one-to-one mapping. The same data word is always encoded as the same code word. This consistency is fundamental for error detection and correction. Next, we'll highlight the critical difference between error detection and error correction. For error detection, we need to ensure that any valid code word is far enough away from all other valid code words. So you make sure that the code words are very dissimilar to each other. So this prevents a single bit error from transforming it into another valid one. We just need to know an error occurred so we can ask for a retransmission. However, for error correction, the requirement is much uh, strict. So we need a coding scheme where a code word with an error is still closer to its original valid code word than to any other valid code word. This allows the receiver to identify and correct the error without a retransmission. So this is essential for channels with very high latency. So if the received word is valid, then we accept it and extract the data word from it. If the received word is invalid, then discard the frame. Some of the limitations are uh, you may miss some errors if corrupted word matches another valid code word. Block coding can detect only single errors. Multiple errors may remain undetected. So we will introduce the concept of Hamming distance as a key metric for evaluating a code's performance. The Hamming distance is a measure of this farness between code words. It is simply the number of bit positions in which two code words of the same length differ. For example, the Hamming distance between 000 and 011 is 2 because two bit positions are different. The minimum Hamming distance of a code scheme is the smallest distance between any two valid code words in that scheme. The power of this metric is that it tells us exactly how many errors we can handle. To detect up to S errors, we need D minimum of at least S plus 1. The uh, and to correct up to T errors, we need a D min of at least 2T plus 1. Okay, we'll continue in the next class.